Dear classmates, welcome back to the introduction chapter. In this video, we are going to discuss important test economics. First, we will see why and who invests in tests. We will also show some statistics in global semiconductor industry. And then we will discuss how to make optimal test decisions. Although testing is expensive, repair cost is even more expensive. According to a book published by Davis in 1982, he observed an interesting rule of 10. That means if we can test an IC and identify a fault, we can simply throw it away. The cost is just 50 cents. However, if we did not do a good IC testing, the defective IC can be assembled into a board. Then we perform a board level testing. If we identify the faulty board, then we need to throw the whole board away. The cost is $5. It can be 10 times more than a defective IC. If we still did not do a board level testing well, then the defective board can be assembled into a system. In the system level, if we identify a fault, then we may need to throw the whole system away. The cost can be up to $50. Which is again 10 times more than a defective board. What is worse, if we sell the defective system to a customer, he may request a warranty or repair, which can be up to $500, which is 10 times even more than the system test. So Davis observed that in each level, the cost of a fault can increase by 10 times. This is what he calls the rule of 10. Very interestingly, this is exactly the same as the old saying, a stitch in time saves 9. That means if we can do IC testing very well, then we can save a lot of trouble in the board level, system level, or in the warranty repair. So now we know that testing is very important. In the global semiconductor market, 15% of the revenue goes to test. According to the statistic by WSTS, in 2016, the semiconductor market is up to $340 billion, out of which 15% goes to packaging and test. Take the Taiwanese semiconductor market, for example. The total revenue of Taiwanese semiconductor market is almost $76 billion, which is about 22% of the global market. Taiwanese contribution to the global semiconductor market is top 2 in the world, second to only the United States. Out of this $76 billion, 20 billion go to fabless design, 41 billion goes to manufacturing, and 14 billion goes to packaging and testing. As is shown in this table, the growth rate of Taiwanese test industry increased rapidly over the past few years. So we can know that test industry plays a very important role in the global semiconductor market. In this semiconductor pyramid, we can see many important companies are investing heavily in tests. On the top of the pyramid, there are many important EDA companies such as Synopsys, Cadence, Mentor. They all provide important EDA tools for testing, such as ADPG and force simulation. In the middle of this pyramid, there are many well-known design houses such as MediaTek, Realtek, NVIDIA. They insert DFT or built-in self-test circuitry so that their designs are easy to test. At the bottom of this pyramid, there are fab companies such as TSMC and assembly test service companies such as ASE. They provide manufacturing, assembly, and test service for the fabless companies. On the left-hand side, we see many well-known IDM companies such as TI, Intel, NXP, and IBM. They all invest heavily in testing because test is essential to the IC quality. This table lists top 3 world EDA companies. In 2016, global EDA market is about $8 billion. All the top companies, including Synopsys, Cadence, Mentor Graphics, provide very good EDA tools for testing. This pie chart shows the EDA market by the tool. The test-related tools are highlighted in box. Totally, these test-related EDA tools are about 5 to 10% of the EDA revenue. In this figure, we can see that testing is an important tool for the EDA companies. In this table, we show the world's top OSAT companies, where OSAT stands for Outsourced Semiconductor Assembly and Test Companies. The world number 1 OSAT is ASE, followed by MCore, SPILE, JCET, and PTI. From this table, we can see that number 1, number 3, and the number 5 OSAT companies are located in Taiwan. So Taiwan made a great contribution to the test industry. Approximately 1/3 of the world's IC are tested by Taiwanese companies. In summary, testing is very important for both Taiwanese and the global IC industry. Now let's discuss how to make optimum test decision. This is a difficult problem since we need to trade off between test cost and the repair cost. Optimum test decision sometimes is not only a technical issue but also an economic issue. We need to trade off between test costs and the repair costs. As is shown in this figure, on our right hand side, we showed tests with high quality. We can see that the blue curve, which is test cost, increases as we improve the test quality. On our left hand side, we showed tests with poor quality. So the green curve, which is repair cost, rises as we lower the test quality. In the middle, the red curve shows the total cost, which is the test cost plus the repair cost. We want to minimize the total cost, so we want to find the optimum test decision. However, different product has different optimum decision, and there is no single best decision for all the product. So what kind of cost can we optimize? From the EDA side, we have many different tools to choose from. Typically, a tool price ranges from 10,000 to 100,000 US dollars. On the designer side, we can choose to insert DFT or bit circuitry. Typically, the area overhead of DFT circuitry is about 5 to 10% of the original design. In the OSAT company side, we can purchase different test equipment. For example, the price of a tester can range from 0.5 to 3 million US dollars. And there are some other equipment such as handler, probe station, and the burning oven. From the user side, we need to rent a tester from the OSAT company. The price is charged according to the test application time. Typically, it's around $50 to 300 US dollars per hour. The test time of a simple ASIC can take 2 to 3 seconds. However, a more expensive CPU can take up to 1 minute. And there are some other costs such as the load board and the probe card. In summary, there are many decisions to make to optimize our test cost. So now let's review a case. In our previous video, we have shown that for a design without DFT, the yield is 98% and the fault coverage is 70%. According to the Brown and Williams model, defect level is 6000 dpm. With DFT, the yield is slightly worse, 97%. However, the fault coverage is significantly improved to 99%. So the defect level is significantly reduced to 300 dpm. We already know that DFT is technically very effective. However, is DFT worth doing economically? We will need some calculation. Continued from the previous slide, this table shows a comparison without DFT and with DFT. Suppose that we manufacture 1 million dies for the design without DFT. For the design with DFT, because the area is larger, we only have 900,000 dies manufactured. The yield of the first case is 98%. However, because the die size is larger with DFT, the yield is slightly reduced to 97%. The fault coverage is 70% and 99%. The defect level is 6000 and 300 dpm respectively. The total sales is equal to the number of die times the yield, and it's $1 per chip. So the total sales without DFT is $980,000 and $873 without DFT. And the repair cost is equal to the number of die times the yield times the defect level times $100 per die. So the total repair cost is up to $592,000 for the die without DFT and only $26,000 with DFT. So in the bottom line, the total profit of two products is equal to the sales minus the repair cost, which is $387,000 and $846,000 respectively. We can see that the winner is the product with DFT. So the answer is yes. It is true for many products that DFT is worth doing. This is because of the Brown and Williams model. Although the yield drops a little bit, the defect level improves significantly with DFT. So DFT is generally worth doing for many different products. Now let's consider a second case. In our previous video, we have shown this typical IC testing flow. First, we perform a wafer test, followed by packaging, and then a final test. You may wonder, why do we need wafer test since we already have this final test? Now let's answer this question with numbers. Let's consider two scenarios. In the first scenario, the yield is poor, only 64%. In the second scenario, the yield is better, 81%. Let's look at the first scenario. In this scenario, we can do it with wafer test or without wafer test. Suppose the total number of dies manufactured are the same, 1 million dies for both cases. The wafer test cost is equal to the number of die times 2 cents. If we do it with wafer test, the wafer test cost is $20,000 for the first case and $0 without wafer test. The wafer test yield is 80% for the first case. Since we don't have wafer test in the second case, so the yield is 100%. And the package cost is equal to the number of die times the wafer yield times 10 cents per die. So it is 80,000 for the first case and 100,000 for the second case. Since we don't have any wafer test, so we need to package every die. And the final test cost is equal to the number of total die times yield times 6 cents per die. This would be 48,000 for the first case and 60,000 for the second case. Because the total yield is 64%, so the final test yield is 80% for the first case and 64% for the second case. In this way, we can calculate the total sales, which is the number of die times the wafer test yield times the final test yield times $1 per die. So the total number of sales are the same, $640,000 for both cases with or without wafer test. Now, the cost is equal to the wafer test cost plus packaging cost plus final test cost. So, the bottom line, the profit is equal to the total sales S minus the total cost C. We can see that the first case with wafer test is larger than the second case. So we have better profit with wafer test. We save some packaging cost because we have wafer test. However, consider the second scenario. This product has very good yield, 81%. They both have 1 million dies manufactured. If we do a wafer test, the wafer test yield is 90%, so the package cost is $90,000. And the final test yield is 90% and 81% respectively. In this way, both cases has the same $810,000. But this time, the cost of two cases are pretty similar. In this case, we can see that no wafer test is the winner because the profit is slightly larger than the case with wafer test. So what is the reason? This is because the yield is now pretty good. So the difference in the package cost is very small. From this calculation, we can know that whether we need wafer test or not, it's really product dependent. It depends on our yield. If we have pretty good yield, maybe we can skip the wafer test. Now it's time for you to take a quiz. We want to determine whether we should burn the IC or not. Suppose that the burning cost is $2 per die, and the burning can significantly improve the quality by 1000 dpm. Suppose that the fabrication cost is 30% of the price and the repair cost is 30 times the price. Consider two different products. The first product is an ASIC. The price per die is $10. Now let's consider testing the ASIC with or without burning. Suppose that we manufacture 1 million dies, and the number of dies sold without burning is 1 million, out of which 1,000 of them are actually defective. If we perform burning, we can throw away this 1,000 dies, so we sell only 999,000 of dies. The total sales is equal to the number of dies sold times the price, which is $10. And the fabrication cost is equal to 1 million dies times $3. The burning cost is 1 million dies times $2 if we do a burning. Of course, it's 0 if we don't do a burning. The repair cost is equal to the number of bad dies sold, which is 1,000 times $300 per die. At the bottom line, we can see that the profit is equal to the number of sales minus all the cost. we can clearly see that the winner is no burning. This is because this ASIC is very cheap. So the burning cost is too much for this ASIC product. Now let's consider a second product, the CPU, of which the price is much higher, $100 per die. Please work on this problem and figure out the numbers in the question mark. Have you got it? At the bottom line, the total cost is equal to the total sales minus the summation of the cost. And the winner is burning. This is because the CPU price is much higher, so the cost of burning is not very significant compared with the other costs. However, the repair cost is much higher for CPU, so it's economically better to perform burning. From this quiz, we can see that whether we need burning or not depends on the price of the product. So there is no single optimum test decision for all the products. Now let's move on to the future of testing. If you think testing is a very old technique, then you are wrong. To test modern designs, we need to improve our test techniques all the time. Here is an example. This figure shows the manufacturing cost per transistor. As we can see, the manufacturing costs keep reducing along the years. However, the blue curve here shows the testing cost per transistor. It remains quite flat over the years. So in 1997, the National Technology Roadmap of Semiconductor predicted that the test cost can sometimes be greater than the manufacturing cost if the historical trend continues. This is very bad news because no one wants to buy a chip of which the test cost is larger than the manufacturing cost. So significant research efforts were applied to push down the test cost. So in the International Technology Roadmap of Semiconductor 2001 version, they revised the prediction. In this new version, the prediction of test cost per transistor is significantly reduced due to research. This example shows the importance of research in testing. So what are the important research topics in testing? Number one is how to reduce the test cost. For example, if we insert built-in self-tests, we can reduce the test equipment cost. If we have good test compression, ATPG, or memory tests, we can reduce the test data volume or test application time. The second important research topic is to improve test quality. For example, if we can have better full model, we can improve the test quality. Or if we can improve the delay tests or design for testability, we can improve the fault coverage. The third important research topic is to improve the yield. If we can diagnose defective IC successfully, then we can obtain valuable information to improve our yield. And last but not the least, we can do research to improve the quality or runtime of EDA tools. Here we show a list of major conferences and journals in the research of testing. This is particularly interesting to graduate students who perform research in this area. For example, the world top conferences are ITC, DAC, and etc. The top journals are Transaction on Computer-Aided Design and Transaction on VLSI System, and etc. There is also a Design and Test magazine for the general audience. In conclusion, in this video, we have shown you why do we need to invest in tests. It is very important to invest in tests because we have a rule of 10s. If we don't detect the fault in the IC level, then we need to pay 10 times higher in the next level. So how to perform the test? The optimal test decision is not only a technical issue but also an economic issue. There is no single best test solution for all the products. So we need to optimize our test for each product. And who should be responsible for good testing? A good testing is not just test engineers' responsibility. It's actually everybody's responsibility to work together so that we can have a successful testing. And this is the final slide in this video. Here we show a famous slogan of IEEE VLSI Test Symposium. The slogan goes like this: without testing, it's a gamble. For example, in the future self-driving car, there are many IC inside the car, and every IC should be tested very thoroughly. If any one of the IC is not tested correctly, then the result would be horrible. In conclusion, testing does and will also play a very important role in high-tech industry. Thank you for watching the video.